Hello and welcome to lecture 25. In last lecture we were discussing about low bypass ratio turbofan engine. We were discussing the benefits of using this low bypass ratio engine in comparison with turbojet engine. Then we were trying to discuss about the limitations in terms of noise, in terms of performance, in terms of efficiency and the size. But that is what is depending on what is our application, where we are using these engines. So, it may be varying as per the requirement. Then we have classified the turbofan engines, and very first engine we have started discussing is forward fan unmixed single spool configuration. For that we have discussed, we have our compressor and fan, they are being routed by turbine, it is a single spool, and other construction details we were discussing about. Then we were started talking about the numerical, where it says we have single spool turbofan engine with having following data, and we need to calculate thrust specific fuel consumption, thermal efficiency, propulsive efficiency and overall efficiency. Here we have bypass ratio of 2, compressor pressure ratio is 8, fan pressure ratio is 2, core mass flow rate it is 15 kg per second, turbine entry temperature is 1400 Kelvin, diffuser pressure recovery factor is 0.98, be careful, this is what is something different. We have combustion chamber efficiency 96%, and it says we are having isentropic efficiency of different components which include fan, compressor, turbine and nozzle are 90%, 88%, 94%, 95%. And there is a loss of total pressure by 3% of delivery pressure for combustion chamber, and total pressure loss in tailpipe is 2%. We will be solving this numerical for the ground level condition, sea level condition, where we will be having our Mach number to be 0. Our temperature and pressure are 288 Kelvin and 101.325 kilopascal. Properties for air and properties for gas are given, and the heating value for the fuel which we are using, it is 43,000 kilojoule per kg. So, in last lecture we were discussing about how do we proceed here. So, very first thing we will be selecting, we will be plotting our line diagram for the engine. Then after we will try to put all these components on TS diagram, and the whole purpose initially it is to calculate the cycle parameters, which includes pressure, temperature, velocity, fuel air ratio, and based on that we will be doing the calculation for the performance of the engine. And that is what is the whole purpose for having such kind of numerical, and that is what we say we are analyzing the cycle. Okay. Now, let us start discussing this thing. So, here if you look at, this is representing our line diagram, where we are having fan, that will be followed by compressor, combustion chamber, turbine, tailpipe and exhaust nozzle. So, just give the numbering accordingly, so that we will not be having confusion here. Okay. So, infinity is far upstream condition, you can say. Condition 2, that is what is the entry of our fan. Condition 8, it is exit of the fan. Similarly, condition 10, condition 9, you can draw actual cycle diagram. I am sure you are able to draw this diagram now. So, what we will be doing is, one by one we will be selecting the components, and we will try to calculate the exit pressure and exit temperature. So, let us start with. So, very first component we have is our intake. Now, for this intake we are given information, it says my diffuser pressure recovery factor is 0.98. We can say this is my total pressure ratio, other terminology. So, I want you to go through week 2, where we have discussed all these parameters. It is slightly different, we are not defining here in terms of diffuser efficiency, be careful. Now, when we say diffuser pressure recovery factor, it is total pressure ratio. So, the thing is here it will be P02 by P0 infinity. What information given to us, it is P infinity and T infinity. So, very first thing we need to calculate is our total pressure at the entry. So, for calculation of total pressure, we know our flow at the entry of the intake, that is what is isentropic flow, and we will be using this relation. So, here in this case, since it is a ground condition and m infinity it is given 0. So, my velocity will be 0, and we can correlate our total pressure and static pressure based on this isentropic relation. Okay. Now, here in this case P infinity is known to us and m infinity, that is 0. So, that is the reason why if you will be putting this number, it says my total pressure at the entry of intake, it is 101.325 kilopascal. Be careful, this is not related with our diffuser efficiency. Now, what it says, we have diffuser pressure recovery factor, it is 0.98. So, let us put that, it says it is P02 by P0 infinity. So, just realize what is the reason why we are calculating our total pressure. So, if we will be putting this number as 0.98, my exit pressure is coming 99.3 kilopascal. So, here on diagram you can say this is my P infinity and this is representing my P02. Be careful about this. Now, next component what we will be calculating, it is the temperature at the exit of the intake, and that is correlated in terms of static temperature and Mach number. Since we have our m infinity to be 0, so it says our exit temperature will be 288 Kelvin. Okay. Now, very first component after my intake is fan, and for fan we are given our fan pressure ratio to be 2, fan efficiency it is given 90%. Since we have our previous temperature and pressure, means entry pressure and entry temperature for the fan. So, based on that we can calculate what will be our exit pressure from the fan. So, this exit pressure is coming to be 198.6 kilopascal. Now, what we know, we have our pressure ratio, we have our efficiency. So, this we will be using for the calculation of exit temperature. So, you know the equation for that. It says my temperature ratio is given by T08 by T02, that we are correlating in terms of pressure ratio and the efficiency. So, if we are putting this as number, it says the exit temperature from the fan is 358.08 Kelvin. Okay. Now, very next component we have is our compressor. Since this is single spool where my fan and compressor they both are on the same shaft. So, let us try to calculate for the compressor. For compressor we are given with the compression ratio of 8, efficiency is 88%. So, based on given information, since we have earlier data, so at the entry of the compressor the pressure will be 198.6 kilopascal. So, just realize this part, say whatever air, compressed air which will be coming out from the fan, that will be entering inside this core engine. Now, there are some ideas where when people they are doing the design of the fan, they are deciding the distribution of the pressure. Say they will say up to certain percentage of my height of the blade we will be having some pressure ratio, and on upper side we will be having some other pressure ratio. That is a design strategy. Okay. Those who are interested can go through the course on aerodynamic design of axial flow compressors and fans, where we have discussed this in detail. So, you will get some other kind of feeling. Okay. So, let us put this number. If we are putting this ratio as say 8, the exit pressure from the compressor is coming 1588.8 kilopascal. Same way our temperature ratio we can correlate in terms of compressor pressure ratio and compressor efficiency. This efficiency it is given as 88%. So, let us put this number. Since my pressure ratio is 8 and efficiency is 88%, we will be getting exit temperature as 688.27 Kelvin. So, this will be the pressure and temperature at the exit of my compressor. Now, very next component we have is combustion chamber, and for this combustion chamber we know in actual case we will not be having combustion to be taking place at constant pressure. So, there is a variation or there is a loss of pressure. It says there is 3% loss, total pressure loss in combustion chamber. So, let us put this number. It says my P04, it is 0.97 into say exit pressure or entry pressure of the combustion chamber. So, here this is coming as 1541.14 kilopascal. Now, here we can write down our mass balance. So, mass balance, it says this is the air which is coming out from the core engine or from the compressor. We are injecting some amount of fuel, and at the exit we will be having this as m dot core plus mf. Now, rather putting this number, let us move towards the energy balance, because that is what is of our interest. We want to do the calculation of temperature and pressure. So, here in this case at the entry condition we know what is our m dot core and H03, that is my exit temperature from the compressor. This is representing our combustion chamber efficiency into mf into lower calorific value of the fuel, and at the exit we can say it is approximately equal to m dot core plus mf into it will be raising the temperature to T04. So, let us put these numbers. If I am writing my energy balance, energy input equal to energy output, and from that we will be calculating our value of fuel air ratio. So, be careful, this fuel air ratio is mf by m core. Now, we have all information available with us. Cp value for the hot gas, it is 1156, maximum turbine entry temperature is 1400 Kelvin. Same way we have temperature at the entry of the combustion chamber, and if we will simplify this thing, so fuel air ratio is coming to be 0.0234. Okay. So, this is the amount of fuel what we are adding in order to raise the temperature to 1400 Kelvin. Just realize this number, just understand this number. Okay. Now, what next component we have is our turbine. So, for this turbine we need to be very careful here. What is the case? This turbine, for earlier case when we were discussing about turbojet engine, turbine it is used to rotate the compressor, but since my compressor and fan they both are on common shaft, that is the reason my work balance I will be writing as work developed by the turbine, that is what will be equal to work consumed by the compressor plus fan. So, let us put this number. Here in this case we can say the work developed by the turbine, it is given by m dot core into 1 plus f Cp T04 minus T05, that is what is equal to, if I am talking about the compressor, then it is m dot core Cp T03 minus T08. Same way for fan we can say what is the amount of air input, it says 1 plus beta into m dot core, be careful. Okay. So, here we need to be very careful in terms of writing this mass flow balance into Cp T08 minus T02. So, let us put this number, and if we are simplifying that, it says my turbine exit temperature is coming to be 940.9 Kelvin. Now, this is what is my turbine. So, if you recall the difference, the major difference compared to your turbojet engine, that is what is happening here. The very next thing we need to calculate is exit pressure, and we know our exit pressure, it is a function of our efficiency. We are talking about the turbine efficiency. So, let us try to correlate that. It says isentropic efficiency of the turbine, that can be represented in terms of expansion ratio, and this expansion ratio we can calculate. This expansion ratio P05 by P04 is coming to be 0.156. Since we know what is our P04, so we can calculate what will be the exit pressure from the turbine, and this turbine exit pressure is 240.12 kilopascal. Okay. So, now we have our exit temperature and exit pressure from the turbine. The next component, it may be tailpipe. Here in this case, since it is given there is 2% loss of total pressure, that means we need to consider the tailpipe for the calculation. So, let us put that number. Here this P06, it is exit pressure from the tailpipe, it is P05 minus delta P. Let us put this number, it is 2% loss. So, that will be 0.98 into 240.12. So, our exit pressure is coming to be 235.32 kilopascal. Okay. Now, in terms of temperature, we know our temperature, this process we are assuming to be adiabatic process. That is the reason my T06 and T05 they both are same. Okay. So, we can say our exit temperature is 940.9 Kelvin. Okay. Now, in terms of nozzle, so here for bypass ratio engine, let it be low bypass ratio engine or let it be high bypass ratio engine. For that we will be having two nozzles which are present. First nozzle, that is what we say, it is turbine nozzle, and second nozzle we can say it is my fan nozzle. So, let us calculate first for the turbine nozzle. So, very first thing again here we will be calculating is our critical pressure ratio. Since my nozzle efficiency is given, that is 95%. So, let us put that number and we will try to calculate what will be our critical pressure. So, when we are putting these numbers, critical pressure is coming 124.08 kilopascal. Now, what is our atmospheric pressure? Our atmospheric pressure is 101.325 kilopascal. So, you can say here my critical pressure it is greater than that of atmospheric pressure. So, we can say this nozzle is choke nozzle, and for the choke nozzle the exit pressure will be equal to critical pressure, and that is why this pressure is coming 124.08 kilopascal. Okay. Now, the next calculation we will be doing, it is for the calculation of exit velocity, because we are interested in calculating the thrust, and the thrust is a function of velocity. In order to calculate that velocity, we need to have exit static temperature. So, that we can correlate based on say temperature ratio, it is given by gamma plus 1 by 2. If we will be putting this number, so exit temperature or exit static temperature is coming 818.17 Kelvin. Since this nozzle is a choke nozzle, for that exit velocity can be calculated as gamma RT9, and if we are putting this number, it says our turbine nozzle exit velocity is coming 552.5 meters per second. Okay. Now, this is for our core engine nozzle. Same way we want to calculate that for the fan nozzle, and we know for the fan the process it is given by from process 8 to 10. So, let us put that. So, here in this case my critical pressure ratio we are writing as P08 by Pc. For the fan nozzle we have efficiency to be 95%. So, let us put this number, and if we will try to calculate the critical pressure, it is coming to be 101.1 kilopascal. So, we can say this is what is say less than that of my 101.325 kilopascal. So, we can say this nozzle as unchoked nozzle. So, for unchoked nozzle my exit pressure will be equal to atmospheric pressure. Though this number is smaller, but we need to be very careful in terms of doing the calculation. Okay. Now, let us see, since we are also interested in what will be the velocity from the fan nozzle. So, for that we will be calculating our temperature ratio. Based on that, we will be calculating what is our static temperature from this nozzle, and this static temperature is coming to 295.44 Kelvin. Here in this case, my nozzle exhaust velocity we are calculating based on 2 Cp efficiency T08 minus T10, and if we are putting this number, V10 or exit velocity from the fan nozzle is coming 345.85 meter per second. So, now we have two exit velocities available with us. Now, in order to calculate our thrust, we know we have two components of the thrust. One, that is what is representing say our momentum thrust, and second component, that is what is representing my pressure thrust. And we know this pressure thrust is a differential pressure into area. So, which area are we talking about? This area is the exit area of my nozzle. So, for the core engine, same way exit area of my fan nozzle. So, let us try to calculate those areas. So, if we will be putting this number, it says for my turbine nozzle, the exit area we can calculate, it is m dot, it is density into area into velocity. We need to be very careful, this m dot 9 is nothing but it is m dot core into 1 plus f divided by V 9 into rho 9. This rho 9 is a density at the exit that we can calculate based on static pressure and static temperature. It is P 9 by R T 9. Let us put these numbers, it is 124.08 into 10 to the power 3 and T 9 is 818.17. So, my density is coming 0.528 kg per meter cube. Now, with this we can calculate what will be the area, and this area we are coming with number say 0.0526 meter square. Okay. Now, let us try for the exit area calculation for the fan. What will be my mass flow rate here? This mass flow rate is m dot 10. What is that m dot 10? It is nothing but what bypass air, that is what is passing through my fan. Okay. So, for that what we know, my bypass ratio we are writing as m dot fan divided by m dot core. So, we need to have what is our m dot fan. This m dot fan we can say it is beta into m dot core. Since my bypass ratio is 2, my core mass flow rate is 15. So, we can say our fan mass flow rate is 30 kg per second. Now, this is what we will be putting in our exit area calculation. It says m10 equal to rho 10 into area into velocity. This m dot fan it is known to us. So, we need to calculate what will be our density. This density we are putting as say P10 by RT10, and this pressure and temperature values they are known to us. So, it says exit density is coming to be 1.195 kg per meter cube. So, just realize the number, this is where we are talking about my density, it is 1.19. Here for the exhaust gas my density is different. Okay. Now, let us try to calculate what will be our area, and this area we are calculating, it is coming as 0.0726 meter square. So, this will be the area from the exit of the nozzle for the fan. Okay. Now, very next calculation we have, it is related with the performance parameters. So, for performance parameter calculation, very first parameter we will be calculating, that is thrust, and that thrust we are correlating as say thrust developed by the cold nozzle and thrust that is what is by hot nozzle. So, that is what we are putting here. For coal it is m dot fan V10 minus V infinity plus A10 P10 minus P infinity Same way for the hot, we are putting m dot core 1 plus f V9 minus V infinity plus this area. Now, almost all parameters they are known to us. So, let us try to put these numbers. V9 we have calculated as say 345.85. Okay. V9 we have calculated, it is 552.5. Fuel air ratio is known to us. Here in this case my nozzle, it was say choke and unchoked nozzle. So, that number you can realize here. So, here in this case if we do the calculation, it says the thrust that is coming to be 20.053 kilonewton. Okay. Now, this we are calculating in terms of say thrust. Very next parameter we have is thrust specific fuel consumption. So, this thrust specific fuel consumption we are writing as m dot f divided by T. It is nothing but f into m dot core, be careful, divided by thrust what we have calculated. Let us put these numbers. Since m dot core is 15, that is known to us, make a habit of writing what all parameters we have taken from the previous calculation, so that you will not commit the mistake here. So, it says thrust specific fuel consumption, it is coming to be 0.0175 grams per Newton second. Okay. Now, we are also interested in calculating the efficiency parameters. So, like we are interested in calculating say thermal efficiency, propulsive efficiency, overall efficiency. So, let us try to do the calculation for that part. Let us put very first thing, it is say propulsive efficiency. Be careful here, the formula for this turbofan engine, that is what is different from the turbojet engine. The thrust that will be replaced by hot thrust and cold thrust. Same way velocity component also will be from my nozzle as well as a nozzle of my core engine and the nozzle of my fan end. Okay. So, here since my V infinity is 0, so propulsive efficiency is coming to be 0. Same way based on thermal efficiency. So, we can say numerator divided by mf into QR. If we are putting this number, it says our efficiency is coming to be 27.4%. Now, overall efficiency what we know, it is propulsive efficiency into thermal efficiency. Sometimes people they used to say thermopropulsive efficiency also. My propulsive efficiency is 0, that is the reason why our overall efficiency will be coming to be say 0. Okay. So, I am sure now for turbofan engine with single spool configuration and that too for the ground condition, you are much more matured. So, as we go ahead, we will be going with the complexity. So, that is the reason here we are discussing about the single spool configuration first. Okay. So, let us try to conclude this part. Here in this case, we have our V infinity 0, pressure and temperature they are given. We have calculated the area of the nozzle from the core engine and area of the nozzle for the fan. We have calculated our net thrust and that is 20.053 kilonewton. Just realize this number it is for single spool configuration. Okay. Same way thrust specific fuel consumption we have calculated, it is 0.0175 grams per Newton second. Propulsive efficiency is 0. Thermal efficiency we have calculated, it is 27.4% and overall efficiency is say 0%. Okay. Here we will be stopping with this numerical, and in next lecture we will be discussing about say next step. So, here what all we are discussing is our ground condition. In next lecture we will try to discuss about say flying condition, where it is flying at particular altitude and at particular Mach number. So, thank you very much. See you again in the next lecture. Okay.